Hello everybody, welcome to today's introduction on the fundamentals of reactive processes. Now that we have performed many material balance problems for processes which are non-reactive, we will move on to performing material balances for reactive processes. In most industries, you would always find some process which involves a reaction. That is how you produce the product. Before we start performing these material balances, we need to understand some of the fundamentals and the terminologies associated with such reactive processes. Let us start with this. Stoichiometry defines the quantitative relationships between reactants and products. Look at this equation. This is a fermentation of glucose to form ethanol. Glucose forms 2 ethanol and 2 carbon dioxide. C6H12O6 gives 2C2H5OH plus 2 CO2. What do you observe here? If you look at this equation carefully, you will see that 1 mole of glucose is reacting to produce 4 moles of products, which are 2 moles of ethanol and 2 moles of carbon dioxide. However, if you were to consider the mass, 180 grams of the reactants, which is 1 mole of glucose, which would weigh its molecular weight, which is 180 grams, ends up forming 180 grams of the product, which is 92 grams of ethanol and 88 grams of carbon dioxide. You also can see that a total of 6 carbon, 12 hydrogen and 6 oxygen atoms are present in both the reactants and the products. What does this mean? We can identify which quantities are conserved. From this, we know that the total mass is conserved and the number of atoms of each of the elements are conserved. However, the moles of the reactants is not equal to the moles of the product. This is an important distinction which we should know. Until now, for non-reactive processes, it would not have mattered whether we wrote the balances either in terms of masses or moles, because the reactions were not taking place and they were not being converted from one form to another. However, from now on, as we perform balances for reactive processes, we need to ensure that the balances are written in terms of masses or as number of atoms of each element. This way we will ensure that the law of conservation is obeyed. We also need to know some terminologies such as stoichiometric quantity. Stoichiometric quantity is the amount based on the stoichiometric coefficients of a balanced equation, and stoichiometric ratio is given as the ratio of the stoichiometric coefficient of 2 reactants in a balanced reaction. So, here is an example problem to help us brush up on the fundamentals related to stoichiometry. The overall reaction for microbial conversion of glucose to glutamic acid is given here. You are asked to calculate the mass of oxygen required to produce 15 grams of glutamic acid. Let us now try and solve this problem. For solving this problem, we need to know the molecular weights of some of the components involved. The molecular weight of oxygen would be 32 grams per mole, and molecular weight of glutamic acid is 147 grams per mole. So, now that we know this, look at the stoichiometry of the equation. It says that 1 mole of glucose reacts with 1 mole of ammonia and 1.5 moles of oxygen to form 1 mole of glutamic acid, 1 mole of carbon dioxide and 3 moles of water. So, 1 mole of glutamic acid is produced by 1.5 moles of oxygen. So, writing this down, we can say that 1.5 moles of oxygen produces 1 mole of glutamic acid, which is C5H9NO4. So, substituting the molecular weights, we can convert these to masses. 1.5 mole of oxygen would weigh 48 grams of oxygen. This would produce 147 grams of glutamic acid. We need to calculate the amount of oxygen which is required for producing 15 grams of glutamic acid. This implies, so 1 gram of glutamic acid is produced by 48 by 147 grams of oxygen. So, therefore, 15 grams of glutamic acid is produced by 48 by 147 times 15, which equals 4.9 grams of oxygen. So, the mass of oxygen required for producing 15 grams of glutamic acid is 4.9 grams. Here is another example problem. When I was talking about the stoichiometry, one of the terminologies I used was a balanced equation. All of us have used balanced equations. We know what balancing an equation is. Usually for chemical reactions, balancing an equation is reasonably simple. However, for biochemical reactions, it might not be that simple and straightforward. To illustrate this and to understand how to perform stoichiometric balancing, we will look at this example problem. Genetically engineered strains of E. coli have become essential tools in production of recombinant human peptides and proteins. One of the first substances synthesized using engineered E. coli was recombinant human insulin or humulin for treatment of people suffering from type 1 diabetes. A simple reaction scheme for the production of humulin is shown below. The bacteria basically consumes glucose under aerobic conditions and produces humulin and also grows to form biomass. So, the reaction is given as glucose plus oxygen plus ammonia forms biomass and humulin, carbon dioxide and water. So, if your experimental observations show that the respiratory quotient, which is defined as the ratio of amount of carbon dioxide released in moles to the amount of oxygen consumed in moles, is 0.5 and the ratio of humulin to biomass production is 1:5, balance the given equation. So, all the information you need for balancing the given equation have been provided. Now, we need to look at how we go about solving this problem. So, to identify the stoichiometric coefficients of all these terms, we will introduce these variables A, B, P, Q, R and S. So, we assume that 1 mole of glucose is taking part in the reaction and we will try to calculate the stoichiometric coefficients for all the other terms, assuming 1 mole of glucose is being consumed during this reaction. So, how do we go about this? What we need to do is we need to make sure that the number of atoms of each of the elements are the same on both the reactant side and the product side. For this, we will start writing balance equations for each of the elemental atoms. So, let us first start writing the balance equation for carbon. So, carbon is entering the reaction through glucose and 6 atoms of carbon is present in the glucose. As we have assumed the stoichiometric coefficient of glucose to be 1, we have 6 atoms of carbon entering. So, the product stream has carbon coming in as humulin and as biomass. So, the humulin coefficient has been given as P, you also have carbon in carbon dioxide. So, using this you have 2.3 times P plus 1 times Q plus 1 times R. So, this becomes your balance equation for carbon. You have 2.3 atoms of carbon in humulin, 1 atom of carbon in the biomass and 1 atom of carbon in your carbon dioxide. Similarly, we will have to write the balance equation for hydrogen as 12 atoms of hydrogen in glucose plus 3 times B atoms of hydrogen in ammonia ends up forming 2.8 times P atoms of hydrogen in humulin plus 1.9 times Q atoms of hydrogen in biomass plus 2 times S atoms in water. We can also write this balance equations for oxygen and nitrogen. Oxygen would be 6 plus 2A equals 1.8 P plus 0.3 Q plus 2 R plus S, and we can write a nitrogen balance as B equals P plus 0.3 Q plus 0. So, there is no nitrogen in the other thing. So, we just have B equals P plus 0.3 Q. In addition to these stoichiometric quantities which we got from the equation, two other information has been provided to you in the problem. The problem statement tells you that the respiratory quotient is 0.5 and it also defines what the respiratory quotient is. It is said to be the ratio of amount of carbon dioxide released in moles to the amount of oxygen which is consumed in the moles. So, based on the reaction we have, we know that the amount of oxygen which is consumed is A moles and the amount of carbon dioxide which is produced is R moles. So, based on the value given for respiratory quotient, we know that we can write R equals 0.5 A. And another information which has been provided to us in the problem is we have the ratio of humulin to biomass production as 1:5. So, this means we know that humulin to biomass ratio would be P divided by Q equals 1/5, which implies P equals 0.2 Q. We now have 1, 2, 3, 4, 5 and 6 equations and we have 1 A, B, P, Q, R and S which are 6 unknowns. Solving these equations simultaneously, we will be able to get the values for these stoichiometric coefficients. When we perform these calculations, we will end up with the following answers. So, A will be equal to 0.697, B will be equal to 1.935, P will be equal to 0.774, Q would be equal to 3.871, R would be equal to 0.348 and S would be equal to 4.142. So, you can perform these calculations and confirm whether the values I have written here are correct, and this would give you an understanding as to how you would balance an equation which has more tedious numbers than the ones you are used to in chemical reactions. So, now that we have looked at simple reactions and biochemical reactions, let us move on to what you would see in an industrial setup. In an industrial setup, the reactions do not go to completion. There could always be one or more reactants which are supplied in excess. This would be because not all reactants are going to be of the same cost. So, you would want to make sure that the reactant which is more expensive is fully utilized. Therefore, you would supply the cheaper reactants in excess to ensure that the more expensive reactants are fully consumed. There can always be side reactions that are occurring, resulting in formation of byproducts which may not be desirable. It is important to learn terminologies which are associated with such partial and multiple reactions, which will help us in performing material balances for reactive processes in an industrial scale. Let us look at some of the terminologies associated with this. Limiting reactant is the reactant which is supplied in the smallest stoichiometric amount, and you have excess reactant which is the one which is supplied at a ratio more than what is required. The stoichiometric requirement is a terminology which is used to define the amount of a reactant that is needed to react completely with the limiting reactant. You also have a term called fractional excess, which is defining how much of the excess reactant is actually supplied and at what fraction it is in excess. So, this is defined as moles present minus moles required divided by moles required. This fractional excess can also be written as percentage excess, which would be fractional excess times 100. You have a term called fractional conversion. As I said, reactions do not always go to completion, which means only a fraction of the reaction, so a fraction of the reactant gets converted to products. So, the fraction of the reactant which actually gets converted to the product is called as the fractional conversion. It is defined as the moles of the reactant consumed to the moles of reactant fed. Percentage conversion is expressed as fractional conversion times 100. There is also another terminology called degree of completion, which helps us understand to what extent the reaction has gone to completion. So, this is defined usually in terms of the limiting reactant. So, it is defined as the fraction or percentage of the limiting reactant which is converted to products. Extent of reaction is another terminology which is used when we perform material balances, and this will also be used when we perform energy balances for reactive processes. So, extent of reaction is defined as the ratio of change in the number of moles of a reactant or a product to its stoichiometric coefficient. So, the equation is given here. So, the number of moles in the final condition minus the number of moles which was present initially divided by the stoichiometric coefficient will give you the extent of reaction. So, extent of reaction is always positive. Why would that be the case? That is because stoichiometric coefficient is positive for products and it should be used as negative for reactants. So, in case of reactants, the final number of moles will be lesser than the initial number of moles. However, your stoichiometric coefficient will be negative, thereby your extent of reaction ends up being positive. For products, your final number of moles would be higher than the initial number of moles. So, your numerator is positive and your denominator, which is the stoichiometric coefficient, will also be positive, giving a positive extent of reaction. It does not matter how you calculate the extent of reaction, which component you use for calculating the extent of reaction, because all the components of the same equation will give you the exact same value for extent of reaction, assuming all of them are taking part only in that particular reaction. Selectivity is another terminology which is used to define how favorable the conditions are to producing one product over other. So, it is defined as the ratio of moles of a desired product formed to the moles of the undesired product formed. This can also be expressed as percentages, and this tells us the process's ability to select the formation of desired product relative to the undesired product. This is a terminology which can be used for optimizing processes in a way that you produce more of the desired product. Yield is another important terminology. Yield can be defined in many terms. It is used to describe the efficiency of a process. So, yield can be defined based on the feed which is given. So, it is mass or moles of a product which is formed divided by mass or moles of the reactant which is fed. Based on the reactant consumed, you can define yield as mass or moles of a product formed to the mass or moles of the reactant fed. And based on the theoretical consumption of limiting reactant, we can define yield as mass or moles of product formed to the mass or moles of product that would have formed if no side reactions happened and all the limiting reactant reacted completely to form the product. So, these are three different ways yield can be defined, and we will look at using these terminologies appropriately while we perform material balance calculations. Here is an example problem where we will try to solve for all the terminologies which we just learned. Semenov described some of the chemistry of allyl chlorides. The two reactions that are of interest for this problem are given here. The species recovered after the reaction takes place for some time contains chlorine, C3H6, C3H5Cl, C3H6Cl2 and HCl. Based on the product distribution, you are asked to calculate the amount of reactants which is fed to the reactor, the limiting and the excess reactant, fractional conversion of C3H6 to C3H5Cl, selectivity of C3H5Cl relative to C3H6Cl2, yield of C3H5Cl expressed in terms of grams of C3H5Cl to grams of C3H6 fed, and the extent of reaction for these two reactions which are A and B. So, let us see if we can calculate all these values. All the information that has been given to you in the problem has been shown here. So, you have both the reactions that have been listed and you also have all the components and their moles in the exit stream. So, now let us try to solve this problem. For solving this problem, the first step is to identify how much of the reactants are actually entering into the system. For this, we need to make an assumption. What do you think the assumption should be? The assumption we would use here would be only the reactants are entering into the system. If we do not have this assumption, we would not be able to solve this problem, as we would have multiple variables with respect to which of the products are coming in and at what amounts they are coming in. So, for that reason, we will assume that the initial condition has only the reactants. So, we start off with the assumption only reactants are entering. Now, based on the equations we have, we know that the exit stream contains chlorine at 141 moles, which is given here, and chlorine is at 141 moles, and you have C3H5Cl which is leaving at 4.6 moles. From the reaction A, we know that 1 mole of C3H5Cl is produced by 1 mole of chlorine. So, this means 4.6 moles of C3H5Cl was produced by 4.6 moles of chlorine. So, in the first reaction we know that 4.6 moles of chlorine has actually been consumed. So, now we have the second reaction through which chlorine could have been consumed. So, again we know that 1 mole of C3H6Cl2 is produced by 1 mole of chlorine. So, this means 24.5 moles of C3H6Cl2 that is present in the exit stream would have been produced by 24.5 moles of chlorine. So, now that we have calculated these, we can calculate the total amount of chlorine which is fed, which is the input. So, we can go back to the balance equation which we had, which is input minus output plus generation minus consumption equals accumulation. As the process is at steady state, we will have accumulation to be 0, chlorine is not generated. So, you have only consumption. So, you end up with input equals output plus consumption. So, the consumption terms are 24.5 and 4.6 and your output is 141. 141 plus 4.6 plus 24.5 would be the input, giving you a value for the input as 170.1 moles. So, this is the number of moles of chlorine which is entering into the system. Looking at these two equations, we know that the stoichiometric ratio of chlorine and C3H6 are 1:1, which means if 4.6 moles of chlorine is consumed by reaction 1 and 24.5 moles of chlorine is consumed in reaction 2, the same number of moles of C3H6 would also have been consumed by these two reactions. Thereby, the amount of reactant C3H6 fed would basically be the amount of reactant which is leaving the system, which is 651 moles plus 4.6 which was consumed by the first reaction plus 24.5 which was consumed by the second reaction, giving you a value of 680.1 moles. So, this would have been the amount of C3H6 fed to the system. So, this gives us the values for the first part. Now, the second part of the problem asked us to calculate which of these two reactants was in excess and which was the limiting reactant. So, the limiting reactant is basically defined as the one which is given in the lower stoichiometric requirement. So, for this we need to identify the molar requirement and the stoichiometric ratio compared to what was being fed. So, the molar ratio in the feed, molar ratio of chlorine to C3H6 in the feed is actually 170.1 divided by 680.1, giving you a value of 0.2501, whereas the stoichiometric requirement is actually 1:1. As the stoichiometric requirement is higher for chlorine and it is being supplied at a ratio lower than the stoichiometric requirement, we can identify that chlorine is the limiting reactant, and C3H6 is actually being supplied in excess. So, the next part of the problem asks us to calculate the fraction conversion of C3H6 to C3H5Cl. So, we know that C3H6 actually takes part in both the reactions. It is getting converted to C3H6Cl and C3H5Cl and C3H6Cl2. So, we need to identify how much of C3H6 actually went into the first reaction to produce C3H5Cl. So, based on the stoichiometry, we know that 4.6 moles of C3H6 actually got converted to form C3H5Cl. So, the fraction conversion which has been asked for basically would be the amount of C3H6 which reacted to form C3H5Cl, which is 4.6 moles, divided by the total amount of total amount of C3H6 which is fed, which is 680.1, giving you a value of 6.76 times 10 power minus 3. So, the next part of the problem is to calculate selectivity. We have been asked to calculate the selectivity of C3H5Cl relative to C3H6Cl2, indicating that C3H5Cl is probably the desired product. So, we will calculate this selectivity as C3H5Cl which is formed to C3H6Cl2 that has been formed. So, which gives you a value of 4.6 divided by 24.5, which is 0.19 moles of C3H5Cl per mole of C3H6Cl2. So, this gives you the selectivity for one product over the other. So, the next part of the problem is to calculate yield. It has also been stated clearly that you have been asked to calculate yield in terms of grams of product formed per gram of reactant fed. Based on this, we will calculate the yield as 4.6 moles of the product C3H5Cl which is formed times its molecular weight, which is 76.45, divided by 680.1 moles of C3H6 which has been fed times 42 the molecular weight of C3H6 which is fed. So, this gives you a value of 0.012 grams of C3H5Cl per gram of C3H6 which is fed. So, this gives you the yield that has been asked for. The last value which you have been asked to calculate is the extent of reaction. So, the extent of reaction is calculated as N final minus N initial divided by the stoichiometric coefficient. So, for reaction 1 we would calculate it as 4.6, which is the number of moles of C3H5Cl which has been formed, minus 0 which would be the number of C3H5Cl moles which has been supplied initially, divided by its stoichiometric coefficient which is 1, giving you the extent of reaction as 4.6. One thing you should note here is we have used C3H5Cl for performing the calculations for extent of reaction. Why? Why not chlorine or C3H6? Because chlorine and C3H6 do not take part just in the first equation, they take part in both the equations. So, to actually calculate the extent of reaction for the first reaction, we need to use a component which is unique to the first reaction. So, we could either use C3H5Cl or HCl. As we have the information for both, we could choose anything, and we have chosen the amount of C3H5Cl and calculated it as 4.6 moles. Similarly, we can calculate the extent of reaction for the second reaction using a component which is unique to the second reaction, which is C3H6Cl2. So, that would be 24.5 minus 0 divided by 1, giving you 24.5 moles. So, these values have been calculated, and hopefully you have now understood how to use this formulae for calculating the terminologies. Now, with the understanding of these terminologies, we will move on to performing material balances on processes with reactions. Thank you.